So to get started on this method of joint example, what we're going to do is actually determine what members are actually zero force members. So as we said before, zero force member is basically a member that acts in a weird way so that there's really no force acting on that member, causing it to be irrelevant. So let's take this for example. So this member BC. So there's a reaction force or an applied force being applied at joint B. So BC must have a reaction force pointing in that direction because that points along the two force member axis, meaning since these are joints, the reaction forces at B and C must lie on the same line of action. Therefore, they must lie on the same line. So the reaction force of BC is being applied in this direction since the applied force is being applied to the right. So this member right here, BC, is not a zero force member. However, if we look at the member AB, the reaction force either be pointing down or be pointing upward. And either way, there's no reaction force balancing this force AB. So what that means is there's no force up here to counteract this force, and since there's no force up there, there's this idea of unequilibrium, or this joint being not in equilibrium. So that means this member AB must be a zero force member, because if there wasn't, that means a force is being applied at B pointing upward, which will cause this joint B to move upward or rotate around some pivot around here. So that means zero force member is AB. And then the same logic will go for CD as well as DE. So what we could say is that CD, AB, and ED are zero force members. Zero force members. So now what I'm going to do is actually redraw this truss into various components or an exploded diagram, and we'll do some force analysis there. So I'll skip ahead to that. You guys could draw your free body diagram as well. So this is how I drew the free body diagram, the exploded view of this truss, and I basically applied Newton's third law to each of the joints. And I forgot to mention that when we're looking at this component of the joint A and joint E, I applied the reaction forces in this fashion. So I said the reaction force of the pin A is being applied in this direction and in this direction. The resultant is whatever direction that the pin A reacts about. And then E is just a roller, so that means the only reaction force is the normal force against it's rolling. So E is pointing directly upward is what I did in my diagram. So now it's just tedious work of going through each joint and just applying the basic equations that we learned earlier, such as the sum of the forces equaling 0. So we'll start off with joint B. So with joint B, what's going to look like is this. So we take the sum of the forces in the x direction and set it equal to 25 minus FBC, and that set that equal to 0, and that would imply that FBC is 25 kilonewtons. And since it's positive, I drew the direction of the reaction force correctly, so BC is actually in tension. So where is BC? So BC is actually in compression, my bad, compression. So this is in compression. And let me just label the joints real quick. So what we have is that the member BC is actually in compression by this equation right here, since BC is positive, meaning I drew the reaction forces correctly. So let me write that out again. So BC is in compression. So the next joint we're going to look at is F, joint F. So let's label that. So joint F, what we get is going to be the sum of the forces in the y direction equal -10 minus FCF equals 0. So we get FCF equal to -10 kilonewtons. And then we have the sum of the forces in the x direction, which equals FAF minus FFE. And we set that equal to 0. So we get that this FAF equals FFE, which we can use later on if we need to. So from this diagram, or from this equation, we see that FCF is negative 10 kilonewtons, meaning I drew the reaction forces of CF in the wrong direction. So that'll be this member right here. So I drew it in compression, so therefore this actually is in tension. So right here I put tension like that. So FCF, or CF, the member CF, is in tension. The next joint we'll look at is joint C. So joint C, we have the sum of the forces in the x direction equal FBC minus FAC times the cosine of some angle theta minus FCE cosine of theta equals 0. So let's see what theta is in the diagram. So theta is actually this angle right here. This is theta, and then we'll define this angle as alpha. And by using basic definitions of angles and trigonometry, we could define theta as this, and this is theta, and this is alpha, and this is theta as well. And the reason why I'm getting this is because this diagram is pretty much the same in terms of dimensions. So this triangle is similar to this triangle, so we could make these angles congruent. So, and this is also a right angle, and this is also a right angle. So by using this triangle, we could define what theta is. So theta equals the tan inverse of 5 or 6 over 5 which equals 50.194 degrees. And then alpha, we could say that's the tan inverse of 5 over 6, which is going to be 39.806 degrees. So with that said, we could manipulate this equation. So we could say that 25 equals FAC cosine of theta plus FCE cosine of theta. And we could do that 25 equals FAC plus FCE cosine of theta. And we could use this later to solve the system of equations that we're going to have. So now we have the sum of the forces in the y direction, which is going to be FCF minus FAC sine of theta plus FCE sine of theta, which all equals 0. So now what we have is FCE minus FAC times the sine of theta, which equals 10. So by solving the system of equations right here, we can actually get FAC equaling to 13.017 kilonewtons, and we also get FCE, which is equal to 26.034 kilonewtons. So what we can say is that since these values are positive, I drew the reaction forces in the diagram correctly. So what we can say is that FAC, or the member AC, is in tension, as correctly drawn here. This is in tension. And member CE, which is this one, is in compression. So we're almost done with this problem. We have to just analyze 2 more joints. So the next joint we're going to look at is joint E, I believe. Yeah, joint E. So what we have is going to be the sum of the forces in the y direction, which equals E minus FCE sine of theta, which equals 0. And then we could set this, we could rearrange this equation to solve for E. So we get E equals FCE sine of theta. And we could plug in those values. So it would be 26.034 times the sine of 50.194. Now, when you plug in values for this equation, make sure you use the same value that you calculated earlier. So we use FCE, that is a positive 26.03. As long as you didn't change the free body diagram, use this same number. So that's what I would suggest you doing. Don't change anything on the free body diagram. Keep everything the same until the very end, and then from there you could change the arrow directions if you really have to. But since we have a positive value, we have to be consistent with all our other equations. So we plug in a positive value here, but we just use the same mathematics that we've been using since day 1. So we move this over, we get a positive FCE, so we plug in a positive FCE here. Okay, So if there was a negative sign, then a negative sign would be here. But since there isn't, we don't have to include that. So just be consistent with what values you use. Just keep everything the same until the very end of the problem. So with that, we could define E to be 15.391 kilonewtons. And then we could do the sum of the forces in the x direction. So what we can do is do FFE plus FCE cosine of theta, which equals 0. And then we do FFE equals negative 26.034. See how I moved this over to a negative, and we plugged in the value for FCE, which is right here, into that equation. So just be careful with your signs and be consistent with your equations. So 50.194 degrees, and what we get is that FFE is negative 16.667 kilonewtons. And since we know that FFE is actually equal to FF or FAF, we could set those equal to each other. So we could say that FAF is also equal to negative 16.667 kilonewtons. So since these values are negative, that means I drew the reaction forces in the diagram incorrectly, which is completely fine. So we have FFE, or FE member is going to be in tension, which is the opposite of what I drew. And then what we have for AF is that it's in tension as well. So that's what we get for tension. And I guess that's all we have to do for this problem. We can solve for the reaction force at pin A, but that's not what we have to do. We only have to determine whether or not the members are in tension and compression, so that's it for this problem. But if you want to find the reaction force at pin A, all you have to do is look at the joint A and then do the basic sum of the forces in the x and y direction to solve for the various reaction forces for pin A. So let's quickly recap what we just did. The very first thing you should always do is actually look for the full free body diagram of the problem, and that would actually save you some time if you want, because I didn't do that in this problem, which is unfortunate and pretty hypocritical of what I just said. However, if you look at the free body diagram of the whole system before splitting it into various members, what you would notice here is that the applied force 25 kilonewtons at point G, or joint B, my bad, and the reaction force at A, we could say of this free body diagram is that the sum of the forces in the x direction is 25 minus AX equals 0. So from there we could actually define what AX is, and that maybe could save you some time when solving this problem. But it doesn't, for this problem, it didn't really matter if you did that or not. But it's always good to look at the full diagram before splitting it up into various components. So, and then the second thing we did, or the first thing we did in this video, which should have been the second thing, is we looked for zero force members. And we saw the zero force member in A, B, C, D, and DE. So that's just the idea that for this joint to be in equilibrium, joint B to be in equilibrium, all the forces have to interact in such a way that they sum up to 0. So since there's a applied force acting in the horizontal direction, the only force that can counteract that is this two force member BC, and that has to lie along this axis right here. So it has to point in the opposite direction, in the horizontal direction. And that means the only direction that this two force member AB can apply is in the vertical direction. And since there's no other force being applied in the vertical direction, there is no reaction force in AB. So that's why it's a zero force member. And that's the same for CD and DE. And then what we did, we exploded the diagram into various members, such as B, C, CE, and so on. And then we applied the Newton's third law to draw the reaction forces onto the joints and as well as the members. And then from there, we looked at the various joints individually and used the very basic idea of summing the forces and setting them equal to 0 for the definition of equilibrium. And we repeated the process and noticed that some values were negative and positive, and then we had to change the direction of the signs or direction of the arrows or the force vectors to determine whether or not they were in compression or in tension. So that's it for this video. Hopefully this video helped. Again, this is the very method of joints is very tedious, and basically repeat the same process over and over again until you have all the members that you need to find for compression and tension. So that's it for this video, and I'll see you next time.